Welcome to our short lesson on dealing with situations that involve diagonal vectors. And we have here a sample of what that might look like. I have vector A that is both to the right and up. We have vector B that is also to the right and up, but we could have ones that would be to the left and up or to the left and down, and the same methods would still generally apply. So we have this problem. We have a magnitude here. We have an angle. And so we've got everything that we need in order to sort these problems out. So we'll have steps that every problem could be broken into. And it's really each of these steps. Often for a problem, you only really need to do one of them. The sample problem that we have that is going to require all three of those is a really rare. Usually one or two of these, and so being aware of what these separate individual things are is pretty useful. So the first one is to turn diagonals into x and y components. So we want to be able to take any diagonal vector that works on two axes, it's right and up or south and west, turn our diagonals into x and y components. And our x and y vectors are much easier to deal with. They can add and subtract with other x and y vectors. We know how to deal with vectors that are perpendicular to each other. So in the previous video we had three different basic vector addition methods, and this gets us into a pretty simple one. So our next basic skill is to combine all x vectors into an x total. And that's just taking all the ones that are right, left. We should hopefully be able to get rid of all of those and just turn them really into one x total vector. And similarly, we want to be able to combine all y's into y total. And you're going to do this a lot. You know, if we have one vector that's up and another vector that's down and another vector that's up, we should be able to combine all of these and get them into really a single 1y vector. A lot of the time, you'll only even have to go this far. Even when we're doing some pretty serious vector work, we could, if we figure out what the total x is and the total y, that's really all you're going to have to do, because it tells us mathematically, it tells us all the really useful information. How much to the right or left is it? How much up or down is it? And going beyond that usually isn't necessary, but in some cases we will need to combine our x total and y total, or just any x and y, into a diagonal vector. So notice how this is the mirror image of step one. Some problems, all you'll need to do is turn your diagonals into x and y components. Some problems, you'll need to combine your x's and y's, and just be very aware that x and y are going to be totally separate from each other, that you'll deal with those completely separately. And that's the main trick for dealing with anything that involves step two. Step three, well, that'll involve a little bit of Pythagorean theorem and a little bit of trig. The good news is you won't have to do it very often, but you should be aware of exactly how you'll handle it if you need to. But I can combine x total and y total. I can reverse what we did in step one and take two perpendicular vectors, x and y, and turn them into a diagonal. And I do want to also be able to find the angle. Okay, so let's look at these in the context of the sample problem. All right, so mathematically, let's get down to it. Step one. If I have vector A, and I actually look at my angle and say, all right, that is 20 degrees above the horizontal, I need to figure out what my AX and what my AY is, and so that's why we practiced taking components. And so if I have 53 meters at this angle of 20 degrees, then I'm going to get some number of meters to the right and some number of meters toward the top of the page. AX, my x component, will be 53 times the cosine of 20 degrees. It's the adjacent one. And once again, if you have a little bit of trouble with that, if you're not clear on why we did that, you can just go back and review the trig video. It won't take very long, and just a little bit of learning will go a long way for that. We could figure out 53 times the cosine of 20. AY will be 53 times the sine of 20. And then we'll plug into our calculator, take a quick break, and check that out. So we'll figure out that our AX is 49.8. Remember, like we said before, this will have the same units as the original. We can only get displacement meters out of meters, and so on. 49.8 meters to the right, 18.1 meters up. For vector B, we'll repeat this process. If I have color coding, I might as well use it. So we'll figure out BX and BY. It said it was 63 degrees above the horizontal. And we figured out, we said this was 34, exactly 34 meters. So BX in this case will be 34 times the cosine of 63 degrees. I hope I've impressed upon you by now that this doesn't have to be cosine for x. It depends on how the triangle is drawn and where the angle is placed in that triangle. We could have 34 sine of 63 degrees for a y, 15.4 meters to the right, and 30.3 meters up. And we've completed step 1, which once again was to take our diagonal vectors and replace these useless diagonals with perpendicular. We have AX, and we have BX, and we have a BAY, and we have BY, and that will allow us to pretty easily combine those. That's going to be our next step. Step 2 is to figure out for our x total and our y total. So we had AX and BX. So 49.8 meters and 15.4 meters. And so if I put those together, I'll end up with 65.2 meters. Now if we combine our y's, AY plus BY, I had 18.1 meters and 30.3 meters. And so when we combine those, I get 48.4 meters. What that means is when we worked everything out here, that we had a total of 65.2 meters to the right and 48.4 meters up. Now, we're working with meters here, but this also works with meters per second squared. This works with any vectors. So, as I said, if you figure out this much, if you figure out the x total and the y total, in a lot of cases, that's going to be all you ever have to figure out. But, in some cases, you will be asked to combine these into a single vector. In other words, combine into our diagonal. That was our step 3. So, okay, if we've figured this out, all we have to do now is take our 65.2 and our 48.4, and one of the lovely things about this is I don't have to worry about drawing it to scale anymore. As long as I know my directions, 65.2 to the right, 48.4 up, I know that these are perpendicular to each other. The resulting vector of these will be the Pythagorean hypotenuse. And so, that's a little messy, isn't it? Let's do it like that. 65.2 squared and 48.4 squared. I figure out that the magnitude of this is 81.2. So I figured out the magnitude. I figured out that the distance from here to here, the change is 81.2 meters exactly. But remember, we also need a direction to go with it. At what angle? And if you draw a little diagram of this, then that will be enough information to figure out, if you calculate a different angle, but as long as you've drawn the diagram, then I will be happy with that, and anybody who's looking at it will be able to tell what you're talking about. The inverse tangent for this is going to be opposite over adjacent. So if I take my opposite, 48.4, over my adjacent, 65.2, and I calculate what the inverse tangent of this quantity is, I will get 36.6 degrees. And so do make sure your calculator is in degrees when you do this kind of problem. But then that will tell us everything that we need to know about this combined vector, this resultant. 36.6 degrees, 81.2 meters for the magnitude. That's it.